This is a video tutorial of CESAR 2D software. Tutorial number 2, Consolidation under embankment. For the detailed support, please go to 3w.cesarlcpc.com. The context and the objectives: an embankment can be built for different types of projects like for road or railways, for dams as illustrated. The aim of this analysis is to get the evolution of the settlement over time. Thus, the geotechnical engineer can check if they are satisfactory for behavior of the embankment or structures around it. 3 different analyses are proposed in CESAR: first, an undrained analysis, second, a drained analysis, and finally, the consolidation or fully coupled analysis. We will now explain them from the finite element method numerical perspective. The hydro-mechanical coupling is the soil deformation due to the effective stresses, where we subtract the pore pressures due to the total stresses. The pore pressure depends from the soil deformation, meaning that if the soil is compressed, then the pore pressure increases. Generally, we cannot analyze separately the deformation and the pore pressure. That's why a coupled analysis is required. This means that this solution is function of the time. On the other hand, in some particular cases, we can carry out semi-coupled or sequential analyses. This type of analysis will consider the hydraulic state separately. It can be established at long term if we suppose that the water skeleton is assumed not to change. In this case, it is assumed that the initial hydraulic conditions are constant. This means that we have a unidirectional relationship. We can report the original hydraulic analysis into the mechanical model. But this hydraulic condition cannot be altered by the soil deformation. In this analysis, the unknown parameter is the displacement field. In addition, the coupled analysis is possible. It requires to solve the coupled equations with the hypothesis of Biot. As a result, the hydraulic and mechanical boundaries are variable. And we have a bidirectional relationship between both hydraulic and mechanical states. Therefore, in this analysis we have the unknown parameters are the displacement field and hydraulic pressure field. For further explanation of the semi-coupled analysis, we detail 2 specific cases, starting with the undrained analysis. In CESAR, 2 methods are proposed for calculation of the undrained state. Method number 1, total stresses analysis. The total stress is equal to the sum of effective stresses plus the interstitial pressures. We use the undrained soil parameters with the module, the Poisson ratio, the cohesion, the internal friction angle, the fluid bulk modulus, and the porosity. Method number 2, same total stresses, but we will use the undrained soil parameters, the undrained module, the Poisson coefficient, close but not equal to 0.5, the undrained cohesion. The undrained internal friction angle is set to 0. In this tutorial we will explain the method number 1 as it is assumed to be more accurate in terms of displacements but do not represent correctly the shear. The second case of semi-coupled analysis is the drained analysis. There, no variation in the pore pressure field occurs, so the total stresses variation depends of the effective stresses variation. We use the drained soil parameters. What you will learn: we start with the geometry initially, we have a soil with 3 saturate layers, then we modeling the embankment. For simplification reason, the geometry of the embankment is symmetric, the model can be reduced to 1/2. In addition, the embankment is modeled by a trapezoidal pressure distributed in a downward direction with respect to the variation of embankment thickness. Moreover, taking into account the length of the embankment compared to its area section, the model can be analyzed in plane strain. We go on with the mesh. Here we use a quadratic interpolation, filling with triangle elements. Staged construction. Stage 1, undrained behavior. Stage 2, drained behavior. Stage 3, consolidation behavior. Initial parameters. Boundary condition. Loading sets, with the embankment as load. Analysis of 2 statics models and 1 consolidation model. Results of the settlement. Headwater and hydraulic pressure. Let's begin with the geometry. In this first step, we tick off link points to get every single point connect by a line to complete the sketch. Tool points to edit all the coordinates described in the support paper. Now, we pick the option, lines, and also, we click in this tool, zoom, we can zoom the model to get a better visualization. To create every layer, simply click opposite points and a new surface is created. The last thing to do is to assign a color to each layer. In this case we have 1, 2, and 3 layers. We pass to the second tab. Mesh. In this step we must define the area of interest. We select the lines of the embankment region, and in the toolbox fixed length divisions we set a 1 meter division, click on apply. And on the outer edges of our region of interest, we set a constant division of 5 meters. Select the edges and click on apply. Now, we must set a progressive division between the area of interest and the outer boundaries. We use the tool progressive length divisions. As first division, we put in 1 meter, and as last division 5 meters. Click on the edges defines the first division location. In that way you will get a horizontal division with a distance from 1 meter to 5 meters. To generate the mesh in the surface, we select the surface meshing tool. Now, we select all the surfaces where we set interpolation as quadratic. And we click on apply. Before going to the properties tab, we create the first static model. First, we make a click right on static. Second, we select the option add a model. Third, we name the model, for example short term, because of the undrained condition. Fourth, the definition of the model, in this case it is defined as initial parameters, and validate. Properties. All the outline properties on this video are from the paper support. The elasticity parameters are of linear isotropic elasticity type, with an undrained behavior that uses 2 additional parameters: the fluid bulk modulus and the porosity. The plastic parameter follows the Moore-Coulombs criterion with the cohesion and friction angle. Once all the data filled up, we can validate to save those parameters. Now to create a new set, we click on add. When we create a new property set, we always copy the information filled up from the previous property set. This means that we must edit and check all the boxes. When all the data of the second layer are input, we proceed with the last layer parameters. Property application. First, we select a layer, then the correspondent material set and we apply. Layer 3, U. Layer 2, U. And Layer 1. After the properties assignation, we go to Initial Parameters tab. We select the geostatic stresses. To fill up this window, we insert 3 lines with insert. It requires the height, the volume weight and the K0 of each soil layer. Remind that we are working in effective stress state, therefore we use the reduced weight to soil below the water table. If we don't have K0, we can use 1 minus sin phi. We fill up all the data and click on validate. To go on with boundary conditions, we use the predefined tool with side supports and fixed base so that we can. Thus, we fix the horizontal displacements of the vertical sides and we model a substratum at the base of the model. Load. The weight of the embankment is modeled by 2 pressures. On one side, between points C and D, we have a uniform pressure of 40 kN per meter. After selecting the segment, we click on apply. And between points D to E, we have a variable pressure. This variable pressure goes from the right to the left. That's why P1 is 0 kN per meter and P2 is 40 kN per meter. Select the segment and click on apply. Following with the stage conception, we define the analysis settings. We make a left click on analysis settings. For the iteration process, we use a progressive increase with a factor of 1/5. While its weight will be increased with time. It is preferable to avoid instantaneous loadings in a coupled calculation and an elastoplastic analysis. This is because the loadings may introduce a discontinuity of the fields of solutions with respect to time, so that they are prejudicial to the stability and the precision. For the solution method we choose the method of initial stresses and the algorithm type Pardiso. We validate. To proceed with the model. To change the load's name, we may click on the load name and we press F2 to rename it embankment self-weight. Following with the stage construction, we add the drained model. This second stage is also a static model. Right-click on the previous model, short term, and select the option, copy. This model will be defined for the long-term state. In this second window, model sharing options. We can share the properties, the boundary conditions and the loadings between the stages. Here, we pick only boundary conditions. And we validate. With long-term model, we must define new properties set as the current properties varies only for the undrained behavior. For the consolidation model, we mark inactive the undrained behavior. Consequently, the porosity and the fluid bulk modulus are not taken into account. For all others parameters, we keep the same values. Here we have a trick for quick addition. As example, if we chose in the list the properties layer 2 property, we will get the same properties filled up. So, a simple change of the undrained behavior for every single layer of soil is enough. We fill up all the boxes, and the end we validate to save. Last layer. To proceed with the properties application. Now we apply the properties to each layer, layer 3D, layer 2D, and layer 1D. The last stage construction, consolidation model. Here we make click right on consolidation, and we select the option to add a model. We call this model consolidation. This model has flow and coupled parameters to be filled up in addition to mechanical properties. After the model creation, we have to apply the consolidation properties. Now the properties involve the flow parameters with the coefficients of the permeabilities tensor at saturation and the coupled parameters with the unit weight of the pore fluid, the porosity and the compressibility of the pore fluid. We use the same trick to modify all the properties without the need of fill up every single box. Layer 2 CD means consolidation. Keep attention on the addition and verify every single parameter. Layer 1 CD. We validate to go ahead with the properties application. To assign the properties, we tick off every single layer with correspondent material. Layer 3 CD, layer 2 CD, and layer 1 CD. We can copy the initial parameters from the first module to this consolidation model by drag and drop. Also, we check if those are the good values before proceeding. The boundary conditions for the consolidation model have to be completed with a hydraulic boundary. We pick on the groundwater area the option constant water head with a hydraulic load of 0 meters. We select the segments at the surface and we apply the groundwater flow condition. For the load, embankment self-weight, we drag and drop the load from the long-term model to the consolidation model. We pick copy. Analysis. The consolidation model is defined by the time. To fill up the number of time steps, we always add 1 plus for the initial step. For example, here we want 50, so we fill up 51. In this case, we put 3 different numbers of steps: 10, 20, and 50. We must put the absolute value, not the accumulation. And the step of values are 5,000, 50,000 and 50,000 seconds, corresponding to 1.3 hours, 13 hours and 5.8 days. The loading is controlled so that we simulate the progressive loading of the embankment under its self-weight. We edit the 10 first steps with an increment of 0.1. The load remains constant for the following time steps. The coefficient of the load set is 1. When we end to fill up all the coefficients with 1, we can validate. Analysis Manager. Check that all the stages are ready and validate. Don't forget to save your file. When the calculation is over, we go on to the results. In this section we choose all the pertinent parameters to see the correct answers. We adjust the settings for the display of the contour plots and the mesh. So on the options bar, click on Contour Plot Settings. Here we set the style on areas and the color set black. Click on Apply. Now we can see the evolution of displacement on the soil. Also, we can set the mesh, so in the mesh settings, we select Group Borders in the mesh borders and we apply. To see the settlements on the soil, we go to Type of Results, and with the deformed model applied and the contour plots active, we choose the total displacement and click on Apply to see the results. Here, we can see the evolution from the first increment with 4.8 mm to the fifth increment with 31.3 mm of displacement. Compared to the long term on the first increment, we had 9.9 millimeters, and, for the last increment, we got 71.6 millimeters. So, if we compare, the last time step, from short term, is equivalent to the 10th time step, with 33 millimeters, and the last time step of the consolidation is like the long-term stage. It has 74 millimeters of displacement. To see the evolution across the time, we can use the tool, Animation, select all entities and click on Play. Also, we can see the hydraulic pressure in the type of result, so change the deformed mesh to undeformed, and the contour plots, parameter we choose, hydraulic pressure. Click on Apply. Therefore, we can apply, on the contour plot settlings, a color scheme corresponds to the groundwater. An excellent way to see this evolution across the time. We use the animation tool. Choose all entities and click play. We can appreciate the evolution of the hydraulic pressure field. It is stabilizing with time as the excess pore pressure generated by the embankment loading is dissipating. To see the settlement on this study, we chose, on type of results, the vertical displacements with the deformed mesh. We apply and we define, in the displacement settings, the deformation scale, manual option. With the scale of 2 mm to 0.1 meters. Click on Apply. To see the correct colors of the plot, we go to Contour Plot Settings and we change the auto scale to manual. We define the inferior value in -72 mm to 1 mm like superior value. And in the color scheme we put CESAR inverse. Click on Apply. Moreover, displaying the total settlements over the time. We go to Animation, tick off all entities, unhook the repetition of the animation and play. We show also how to get the water head load in the mid layer. Go to Charts and Active Points on the entities for Chats toolbar. We created 4 points. The first, center of embankment line. The second, edge of embankment line. Third, mid position of layer 1 and last one mid position of layer 2. We activated set of points. We assign mid points as name of the set. After that we choose the point P2 and P3 and click on Add. To see the graph, go to Chats for a set of points. On set of points, put the options head water in y-axis and mid points like reference and click on Apply. In this graph we can see the evolution of water head in the mid points over the incremental time steps. To show the vertical displacement on the embankment line, go to Lines and click on the point P0 and the point P1. Click 2 times on P1 when the line became red, it means that it's well defined. Now to assign a name we use the tool line set, we apply a name, for example embankment. To add this element, we select the option, Not Selection, on the toolbar. And we made click on the line defined between P0 and P1. Click on Add. To display the graph, click on Charts for a line set. On the y-axis, we put the displacement on y. In this case we compare the time steps 0, 10, and 50. And click on Apply. Again, we can compare the maximum settlements obtained at time steps 10, end of the embankment construction, and 50, to those calculated during the short-term and the long-term analysis. They are very close, validating the two methods of calculating settlements in soils under embankment load. Using the data export feature, we can generate a file for external analysis of our results. Doing so, we generate this graph, settlement over time, from the consolidation model, and we plot the results of the short-term and long-term analyses. All 3 analyses are relevant for evaluation of embankment settlements. Thank you for watching us. For more information go to 3w.cesarlcpc.com.